So as we've already noticed, and we've talked about in class, the entropy changes are affected by the temperature that the system is at. If you put ice in a warm room, it will spontaneously melt. If you put water in a cold enough environment, it will spontaneously freeze. No matter what the endothermic or exothermic is, the temperature is what is really driving the spontaneity. And so when we're looking at the change in entropy, we need to look at the temperature and the endothermic and exothermicness of what's going on. So an exothermic process is favored if the surroundings are at a low temperature, right? Because it's giving off heat. Heat is being pulled out of it. So when ice is freezing, water is freezing to make ice, that's exothermic. That's spontaneous if the temperature of the surroundings is low enough. So if we change that around and look at the entropy change, the delta S of the surroundings depends on the temperature. And the formula that we use is negative delta H, or the opposite of the entropy change, divided by the temperatures. It's an inverse relationship. So to combine those two ideas, the enthalpy and the entropy, we use what's called Gibbs free energy. Why is the energy free? It's energy that's free to do work. There's energy that is useful to do work and energy that's not useful to do work. The Gibbs free energy, named after the guy who figured this out, is energy that is available to do work. It's free energy to do work with. And he figured out the equation, G, the Gibbs free energy, is equal to H, the enthalpy of the system, minus temperature times entropy. But of course, we can't measure just the enthalpy of the system. We always measure the enthalpy change. And we never measure the entropy of a system. We measure the entropy change in the system. And so we use the deltas. Delta G, the change in Gibbs free energy, is equal to delta H, the change in enthalpy, minus T, the temperature, times delta S, the change in entropy, at a constant temperature. So if we do a little bit of algebraic manipulation with this, we just kind of mess it algebraically. If we divide everything by negative T, we get negative delta G over T equals negative delta H over T plus S. So if we look at that negative delta H over T, that was equal to, from the previous slide, the delta S of the surroundings. So negative delta G over T is equal to the change in entropy of the surroundings plus the change in entropy of the system. Well, surroundings plus system is the universe. So delta S of the universe is negative delta G divided by T. That has to always be positive for spontaneous reactions to occur. Delta S of the universe has to be positive. So if delta G is negative, at a constant temperature and pressure, the process will be spontaneous. If delta G is positive, that means it's negative of positive. It's negative delta S of the universe. That doesn't work. That can't be a spontaneous change. So we're always wanting the Gibbs free energy to be negative, no matter what the temperature is, no matter what the enthalpy is, no matter what the change in entropy is of the system. As long as the Gibbs free energy change, delta G, is negative, the process will be spontaneous. So let's take a closer look at ice melting. This is the reaction here, water solid going to water liquid. Delta S0 for that change from solid to liquid is positive 22.1 joules per Kelvin mole. Now that makes sense. Solid to a liquid is a positive entropy change. It's getting more disordered. Delta H for that, the enthalpy change, is 6,030 joules per mole, or 6.03 kilojoules per mole. So we can calculate delta G at 10 and negative 10 degrees Celsius. Be careful. We're using actual temperatures here, so we have to change Celsius to Kelvin by adding 273. So if we use the equation, delta G is delta H minus T delta S at 283, that's the positive 10, and 263 Kelvin, we can figure this out. So get your calculators, get this written down. Delta H is 6,030 minus, and for positive 10 degrees, we'll use 283 Kelvin, so 283 times the delta S0, that's 22.1, and you should get negative 224.3. That would be a spontaneous process because delta G is negative. Now if we take it to negative 10 degrees Celsius, so we'll clear the calculators, and again we take the same delta H, 6030, minus, the temperature this time we'll use 263 because it's negative 10, so 263 Kelvin times the delta S0 of 22.1. We end up with positive 217.7. Positive delta G means it's not spontaneous. It's only spontaneous in the reverse direction. So this makes sense to us. At positive 10 degrees, solid to liquid spontaneous. At negative 10 degrees, the reverse is spontaneous, and the delta G calculations show us that. From this, we can build this table. This is a table that you will be expected to reproduce or understand or figure out again on a test. So if we're looking at spontaneity, so we're looking for negative delta G's. If delta S is positive and delta H is negative, that means both terms are going to be negative. A negative delta H minus the delta S, negative minus something will make it even more negative. So that will be spontaneous at all temperatures. And that makes sense. If delta S is positive, that means it's getting more disordered. Delta H is negative, the heat is flowing out, which we know tends to make things more stable. That's spontaneous at all temperatures. If they're both positive, if the entropy is increasing, which is spontaneous, tends to be spontaneous, but it's endothermic, then we have to look at the temperature. So at lower temperatures, it works. At higher temperatures, it doesn't. If they're both negative, if the entropy is decreasing, but it's exothermic, that works at higher temperatures. And then if the delta S is negative, in other words, it's becoming less disordered or more ordered, and the delta H is positive, it's endothermic, it will never be spontaneous. Ever. Ever. Never. Ever. The temperature change depends if both are positive or both are negative. Then the temperature matters. If it's more disordered and exothermic, always spontaneous. Less disordered and endothermic, so negative delta S, positive delta H, never spontaneous. Otherwise, you have to actually use the equation to figure it out.